engineering teams routinely swap API keys, jumping from GPT-4o to Claude to Gemini, trying to force an agent to complete complex coding tasks. Yet even with these hardware and model upgrades, the agent's failure rate remains exactly the same. Then, on Terminal Bench 2.0, an AI agent suddenly jumped from outside the top 30 all the way to the top 5. The base model running that agent never changed. The performance increase came entirely from the surrounding infrastructure. An agent equals a model plus a harness. Obsessing over base model benchmarks misses the structural problem. A powerful CPU cannot do useful work if it runs on a broken operating system. A naked language model is a stateless text predictor. It cannot execute code, it forgets its state, and it lacks memory. The harness is every piece of code, configuration, and execution logic in the system that is not the neural network itself. This infrastructure includes system prompts, execution sandboxes, middleware, and file system constraints. By layering these tools around the stateless predictor, the system gains the capacity to maintain context, run logic, and operate as a state-aware operating system. Building reliable AI workers requires engineers to stop writing flowery prompts and start rigidly architecting this infrastructural harness. The first architectural layer of this harness establishes state and execution. The industry reflex is to use complex vector databases for agent memory. This adds unnecessary abstraction. The pure, standard file system provides the ultimate, durable, long-term memory primitive for maintaining context across multiple sessions. To act on that memory, the harness grants the model generic bash and code execution capabilities. Giving the model a raw shell allows it to write and execute its own dynamic scripts to solve problems on the fly. This is far more adaptable than hard-coding dozens of static, highly specific tools. Warning tone. However, allowing an autonomous agent to execute arbitrary code directly on a host machine poses a catastrophic security risk. The harness mitigates this by wrapping all execution in an ephemeral cloud container, or Docker sandbox, ensuring strict isolation and enabling horizontal scaling. With a structured file system and a secure sandbox in place, the model now possesses durable memory and physical hands. The second layer is context engineering, necessary to handle workflows that stretch over thousands of operations. As a task progresses, the language model experiences context rot, a measurable degradation in its reasoning abilities as its context window fills with lengthy tool outputs and execution logs. This often triggers a behavioral symptom called context anxiety, where the model prematurely wraps up a complex task simply because it senses its token limit approaching. The harness counters this with compaction, a middleware process that intercepts the context and summarizes conversation states just in time to free up space. When compaction isn't enough, the harness employs a mechanism known as Ralph loops. A structural hook intercepts the model's early exit attempt and physically flushes the current working state safely down to the hard disk. The harness then re-injects the original prompt into a perfectly clean context window, forcing the model to pick up where it left off and continue the task. Middleware does not make the neural network smarter. It artificially extends its attention span to guarantee the model survives long-horizon workflows. The third layer addresses the inherent non-determinism of language models through cybernetic governance. Applying classic control theory to AI engineering reveals a clear directive. Because an LLM cannot be perfectly predictable, the harness must act as a cybernetic governor to keep it on track. This requires feed-forward controls, or guides, which are strict pre-execution boundaries designed to prevent errors before a single line of code is written. For example, the harness can enforce sprint contracts, forcing the agent to define exact testable criteria for what done looks like before starting a subtask. It also requires feedback controls, or sensors, which are post-execution verification mechanisms to catch the inevitable hallucinations. This CI/CD pipeline matrix maps the two parallel tracks used for this. The top track consists of fast, deterministic computational sensors, like custom linters and AST analysis, which run in milliseconds to catch structural violations. The bottom track relies on slow, probabilistic inferential sensors, using a secondary LLM as a judge to evaluate whether the semantic goals of the sprint contract were actually met. Anthropic tested this while building a complex digital audio workstation. A single, isolated generator LLM completely failed to build functional software, repeatedly leaving core components disconnected. By updating the harness to include an autonomous evaluator LLM equipped with Playwright, the system tested its own UI, found its own bugs, and created a self-correcting loop that successfully delivered the software. True reliability in production AI relies on engineering a system that forces immediate autonomous self-correction the moment the model strays from the plan. Currently, developers manually tweak middleware, rewrite intricate system prompts, and configure custom evaluators. This process is highly fragile. Human-designed harnesses suffer severe code drift and logic clashes as tasks become more complex and interactions overlap. The solution is agentic harness engineering, or observability-driven evolution. The architectural prerequisite for this is strict decoupling. The harness must break down into explicit, version-controlled, file-level components. During testing, agents generate millions of tokens of raw trajectory logs, which are entirely too noisy for humans or models to extract meaningful improvement signals from. The system solves this through experience observability, relying on a module called the Agent Debugger. This flow diagram illustrates the data reduction process. The debugger compresses the chaotic millions of raw trajectory tokens, distilling them down into layered, drill-down root cause evidence. By turning log noise into structured, readable evidence, the agentic system gains the ability to read and understand the specific flaws in its own infrastructure. This enables decision observability. An Evolve agent reviews the root cause evidence and writes a falsifiable edit manifest to update the harness components. The system employs an automated rollback mechanism. If an edit to the middleware or prompt fails to improve the pass rate, on the next execution cycle, the system automatically reverts the change. In a recent study on Terminal Bench 2, this automated, self-correcting loop completely surpassed human-designed state-of-the-art harnesses like Codex. Achieved using the identical base model, the left chart shows AHE's massive pass rate increase. The right proves this evolved harness consumed 12% fewer tokens on SWE bench verified. Effective middleware prevents prompt bloat, stopping the agent from constantly rederiving basic engineering rules. The future of AI engineering is not waiting passively for a smarter neural network. It is actively building the cybernetic infrastructure that disciplines any model into a reliable, deterministic worker.